the what we lovingly refer to as the real world. How's everybody doing today? John Barba here with Jason Cox,
How is everyone?
your friendly neighborhood Takeo trainers, and we're here to talk to you about three-speed circulators. Maybe sounds a little old school, you know. I thought this is an ECM world. Well, it's becoming an ECM world. But we're going to talk about three-speed circulators and then go to three-setting circulators, and then maybe get into some of the bigger dogs in terms of ECM and see how they fit, etc. So, and welcome everybody. So glad you could be with us on this Takeo Tuesday as we are officially heading into fall. Today was maybe these past few days. I don't know about where you are, Jason. These past few days
Yep.
have been the first days that really felt like fall here in New Hampshire.
You kind of feel
Rainy.
rainy, and that you feel the little bit of chill in the air, a little bite to it. Yep.
In general, just miserable. I guess that's just the way I look at it, because summer's gone. Anyway, thank you all for joining us. We got about 50 online right now, with more coming in. Do me a favor, if you could do it, just give us a hi, hello, how are you in the chat question section, and just chime in on who you are and where you're from. That way we know you can hear us. That's the most important thing. And we also know that you know how to ask questions and stuff. So Steve says, chiming in. How you doing, Steve? We got Mark chiming in. Okay. Brian's glad to be here. We're glad to have you here, Brian. Anyway, great. We're happy you're with us. And as always, I hope this is going to prove to be a fun and interesting session for you. We got a lot of material to cover. And as always, I always tell people, you want to get the most out of a webinar. Treat it as if we were in a classroom together, meaning ask questions and take notes, write stuff down. It's really easy to kind of lose your focus in something like this and say, all right, yeah, blah, blah, blah. We start sounding like the adults in Charlie Brown, right? Wah, 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 while you're off checking email or something else. And that's cool if that's what you want to do. But if you want to get the most out of this, pretend we're in a class together and I can actually see you, okay? And you're taking notes, writing stuff down and asking questions. That's going to be the most useful thing I think you can do. Anything else you want to add there, J-Dog?
No, I will keep a close eye on the chats here and interrupt you politely anytime something comes up.
Very good. And I got to tell you, this is probably the first time in my 65 years I've ever called anyone J-Dog. So I feel good about that.
I feel honored.
It never really occurred to me to do that, but now I have.
Very good.
Excellent.
Good.
So great. We got Long Island chiming in. We got Canton, Ohio, one of my favorite towns. Love the Pro Football Hall of Fame. That's a great town to be from. And well, let's get started. And again, our discussion is going to be a deep dive on three-speed circulators, three-setting circulators, and we're going to be looking at things like the 0034ePlus, really getting into some bigger circulators and see what the applications are for that. So do three-speed circulators still have a place in an ECM world? I think that's a really good question. We've talked about it before on Takeo Tuesdays, but if you haven't heard it from us already, the Department of Energy has given its final edict, and as of May 22nd of 2028, those guys on the left on your screen, the standard AC typical circulators, the 0015, the 007, all your favorite 00s, plus all your favorites from every other manufacturer, are going to go away. We as manufacturers will not be allowed to make them anymore after May 22nd of 2028. Reality, we're probably going to stop a little bit before that as we ramp up to meet the demand for ECM, and it's actually something we're doing. We've started already, kind of to ramp that up and adding to our manufacturing capabilities. That does not mean you won't be able to get them. We just can't make them anymore, and we can't have any in our buildings. So reps will have them, wholesalers will have them, and reps and wholesalers and you as contractors can sell and install them until you run out. Okay, that's just the way it is. But as of that date, we will no longer be allowed to have anything. We will not be able to have finished product in our facility anymore. So I'll be out the door and off the books. But that's 2028. So that's about 2.5 years from now. So a long way in one respect, not that long in another respect. So just make sure you're kind of aware of what's going to happen. So with that, do three-speed circulators still have a place in the world? Now, here's a provocative statement for you. I've been on record of saying this, and I'm not going to back down from it. I think three-speed circulators, three-speed AC circulators, might be one of the worst things the circulator manufacturing industry has done to you. The promise when they first came out in the early 2000s was, hey, this circulator doesn't have one speed. It doesn't have two speeds. It's got three speeds, man. It's got three speeds. This, on paper, is the only circulator you'll ever need. And on paper, that is in fact true. It is the only circulator you'll ever need on paper. But we don't install circulators on paper, do we? We install circulators in the real world, and we connect them to real systems and real boilers. And these real systems with real boilers have real dynamics that need to be understood. And sometimes those dynamics will conflict with three-speed circulator. It was a nice story. Hey, wholesalers keep this on the shelf. This gets rid of so many SKUs. Contractors keep this on the truck, makes pump size and breeze, just put in the same pump and change the speeds. That's all well and good. It's a great story. It's largely nonsense, but it's a great story, and it proved to be very successful to the point where a lot of people, that's just their go-to circulator. The problem is in a lot of the systems the traditional systems that we have here in North America, it doesn't fit quite right. I mean, it fits in that, yes, we will keep people from freezing to death, but it doesn't fit in that we may be creating problems that we weren't experiencing before, and then we have to address. So again, provocative statement, but one that we do stand by. I think three-speed circulators might have been the worst thing we ever did to the industry, and that's a universal. All of the circulator manufacturers jumped on this horse because it seemed like a great idea. But we learned, and oddly enough, ECM technology actually pulled the cover off of this and really showed us that there's a much better way to pump these systems. But three-speed circulators do have a place. And again, I love this because people ask me, why do you say that? And I say, well, if my answers frighten you, then you should cease asking scary questions. We got to understand the dynamics. Once you understand system dynamics, it becomes very clear that your traditional three-speed circulator has some shortcomings that we can address with ECM 3-setting circulators. Always enjoy asking people this question when they say, oh, I use 3-speed circulators. Well, great. I'd like to know why you use 3-speed circulators. And it's still actually very interesting to me is that people will consider a 3-speed circulator. When I ask, do you use variable speed circulators, they say yes, but what they mean is 3-speed circulators. A 3-speed circulator is 3 fixed settings. Okay, 3 specific speeds that we can click, we can go to. A variable speed circulator is one that will vary its speed based on changing conditions automatically, which requires an ECM technology. So just so we understand the difference. So I love asking this question, why do you use 3-speed pumps? And for you folks out there, if you use 3-speed pumps, just type on in, why do you use 3-speed pumps? No judgment, this is a judgment-free zone, of course. But what I'm asking is what's your reasoning behind using 3-speed pumps? And these are some of the better answers I've gotten over the years. One was, they make pump selection easy. Well, they surely do. You just pick this one pump and pick the right speed. Well, that's a little easier said than done, but that's one of the reasons it makes pump selection easy. I don't have to choose between a 006, a 007, a 008, a 009, blah, 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 blah. I just one pump, 3 speeds, get her done. In the broad sense, yes. In a micro sense, not so much. All right. I got this one from my cousin, actually. He said he loves 3-speed pumps because of the value. And I go, what do you mean? He says, well, it costs the same as a single-speed pump, so I'm getting 3 speeds for the price of one. It's a better deal. It's a better value. Okay, I can understand that. But I also had to point out to him, every job I've ever been to of yours, you always set the thing on high. So what's the point? And that's when he told me to leave. Anyway, my favorite, this is actually my favorite one. Why do you use 3-speed pumps? It's because there aren't any 4 speeds. If there were 4 speeds, I'd use that, doggone it. Okay, great. It's like in I think in a Spinal Tap, 4-speed. It's one faster. You see, it's got one faster. Well, maybe not. I don't know. But that was one of my favorite answers. Why do you use 3-speed pumps? Because you don't make any 4 speeds. Okay, cool. And speed selection. Speed selection's always interesting. Speed selection. How do you choose which speed to go? Once, low, medium, or high? Well, guy told me this. I start at high, and if it makes noise, I turn it down until it stops. Okay. That's choosing the correct speed in terms of noise, but not necessarily the correct speed in terms of requirements. Okay, there's not a lot of math behind that. All right. Then on the other end, I get guys say, well, I start it low and I turn it up till it starts making noise, and then I turn it back one. Okay, same thing, only different. There's not a lot of math there. There's not a lot of, what's the flow, what's the head, what do I need to do? And then I like this one. A guy said, if it's a gas boiler, I put it on high. If it's an oil boiler, I put it on low. And if it's on an indirect, I put it on medium. I said, okay, why? He says, because it works that way. Okay. If it works, it works. That's, you can't really deny that. But how is it working? What is it doing? If works is defined as no one's freezing to death and blaming me, well, that's a pretty low bar. Okay, that's a pretty low bar. I think we can do better. All right. My personal favorite, after careful calculation of flow and head, I select the speed which has the pump curve that best covers the requirements of each job. Nah, nobody says that. Nobody says. Well, yeah, there are plenty of people who do say that, and I appreciate that, but very rarely do I actually get that in terms of a true explanation or a true reason for using a 3-speed pump. What they're doing is guessing. Okay, what most people do is guess, and I love this quote from Sir Arthur Conan Doyle, the man who came up with Sherlock Holmes. I never guess. It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. And we see that an awful lot in hydronics sometimes. We do see that an awful lot. We got to know, okay, there's math. Okay, we got to know flow, we got to know head, then we can make a good decision. So do the math. It's not going to hurt. It's not going to hurt. We start with the universal hydronics formula. We've talked about this many, many times. GPM equals BTUH divided by delta T times 500. That gives us the flow rate we need to deliver the BTUs required under the circumstances with which we're dealing, okay? So the universal hydronics formula, GPM equals BTUH divided by delta T times 500. And if we want to estimate head loss, this is the easy way to estimate head loss. There's a better way to calculate head loss, but this will get you in the game. This will get you in the ballpark. Is you have the you estimate the length of the run, and by the length of the run we mean from the goes out side of the circulator all the way around to the goes into side of the circulator. All right, that's the estimated length, and you estimate as best you can, especially if it's a circulator replacement. We've all been in buildings that where we ran pipe under construction, or we've seen it happen. We can estimate based on our experience and our knowledge. We can estimate that to a fairly accurate degree. 100% accurate, no, but fairly accurate. We can do that. So we might be going from the goes out side of the pump, saying, I'm going up 5 feet. I'm going over 10 feet. That's 15 feet. I'm going up 10 feet. That's 25 feet. I'm going down 20 feet. That's 45 feet. I'm going over 20 feet. That's 65 feet. I'm coming back 20 feet. That's 85 feet. I'm coming over 20 feet. That's 105 feet. I'm coming down 20 feet. That's 125 feet. That's about as good as you can do. All right. If the number ends in anything other than a 0 or 5, you've put too much work into it. All right. We estimate as best we can. Once we have that estimated length, we're going to multiply it by 1.5 to give us the TDL, or total developed length. Total developed length. That takes into account fittings and valves and stuff that's in the way. Fittings have pressure loss that are equal to equivalent lengths of pipe. For example, a 3/4 inch copper elbow will have the same pressure drop as 2.5 feet of straight copper pipe. A 45 will have the same pressure drop as 1 foot of pipe. A full port ball valve will have the same pressure drop as 2.2 feet of pipe, and so on and so on. So we have to allow for that because we can't count them. So we add 50% to the length. That takes into account fittings. Once we have that TDL, or total developed length, to estimate the head, we're going to multiply by 0.04. And 0.04 represents 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. This little math helper will allow you to estimate the head loss on the high side. Always going to be safe, man. Always, always, always going to be safe, because we're estimating the head loss at the maximum flow rate for each size of pipe. So estimate the length, multiply by 1.5, multiply by 0.04. Write it down, learn it, live it, love it, and you'll have it. Is that right? Is that right? So also, just those asterisks will not harm puppies, kittens, or bunnies. All right, so don't worry about doing the math and killing a bunny, a kitten, or a puppy. All right, just it won't happen. It's very safe to do the math. Very safe to do the math. All righty, so here's two of our key 3-speed circulators: the 0010, which is a flat curve circulator, meaning high flow, relatively low head, flat curve. The 0010 was designed to be a replacement circulator for, let's say, the B&G 100 or the Takeo 110, the old three-piece circulators that were on the return side of older boilers. You have to replace that circulator, it finally dies. 0010 very closely emulates the performance characteristics of those circulators. Okay, we go out to really high flow rates, really low head. They're flat curve pumps. They work terrific in those applications. The 0015 is a lower flow, higher head, steeper curve circulator. 15 Bellingossett's NRF22, Grundfos 1558. They're all kind of the same basic performance curves. They've proven to be, you know, kind of the most common performance curves in the industry, but they're also the most problematic because they're steeper. They're great for radiant floor heating, great for anything using PEX where you have, you know, lower flow but higher head. In zone valve applications, pump curves like the blue ones here can be problematic, and we're going to go through that illustration in just a few minutes. Again, we're going to get into the details of speed selection because everybody has their own rationale for just choosing, you know, high speed and being done with it. One thing is that, hey, one person told me, I said, hey, I've got a really big zone of fin tube baseboard. That's got to be high speed. That's a lot of BTUs. It's a long run. I got to use high speed there, right? Well, the math will tell us an interesting story. So let's say I've got a single zone of baseboard with 30,000 BTUs. And if you think about it, 30,000 BTUs is a big honking zone. Okay, 30,000 BTUs is a big honking zone. All right, that's about 55 feet of baseboard. If you think about it, that's a good size zone, man. That's a good size zone, especially when you think about it in the terms of the overall heat loss of a structure. So 55 feet of baseboard, we do the math, we estimate our total run, including the baseboard, comes out to 130 feet. So we've got enough information right here to actually figure out our flow and our head. Jason, I see a question here from Rick. What question do we have? Oh, I'm sorry. Yeah, you're on mute there, Buckaroo. That's $10 in the jar, brother.
Happens to everyone occasionally. Yeah, no, just not to go back, but the 0.04, what is that for again?
The 0.04 represents, well, I'm looking over here because that's where I have the, let me move this over here. There we go. 4 feet of head loss for every 100 feet of straight, properly sized pipe. So 0.04 is 4 100s, right? So it's 4 feet of head for every 100 feet of straight, properly sized pipe at the maximum flow rate for each size of pipe. So our maximum flow rate for 3/4 inch copper is 4 gallons a minute. All right, and this is a copper black iron kind of number here. PEX is different. You got to look at the PEX charts to figure it out for PEX. But 0.04 represents 4 feet of head for every 100 feet of 3/4 inch copper pipe at 4 gallons a minute. 0.04 also represents 4 feet of head for every 100 feet of 1 inch pipe at 9 gallons a minute. It also represents 4 feet of head for every 100 feet of 1.25 inch pipe at 14 gallons a minute, and 4 feet of head for every 100 feet of 1.5 inch pipe at 22 gallons a minute. If the flow rate is less than those numbers, like say, like in this example, I can tell you right now, we're going to have 3 gallons a minute going through 3/4 inch pipe. That's 3 gallons a minute is less than 4 gallons a minute. The actual calculated head, if we do the arithmetic the right way, the actual head will be considerably lower than the number we get when we do this formula. So the formula is a quick, fail-safe, really safe, not exaggerated, but a lot of fudge factor built into it number. Okay, let me know if that is. Oh, he says you got it. Okay, good.
Awesome job. Thank you.
Great. All right, well, let's do the math here and figure out what we have. All right, for flow rate, GPM equals BTUH 30,000 divided by 20 times delta T times 500, which is 20 times 500. So 30,000, 20 times 500 is 10,000. 30,000 divided by 10,000, that gives us a flow rate of 3 gallons a minute. That's not a lot of flow, man. 3 gallons a minute. 30,000 BTUs with just 3 gallons a minute. That's not much if you think about it in the big picture. So 3 gallons a minute is my flow rate. Now my total length, estimated length was 130 feet. So multiply that by 1.5 and again by 0.04. If we math all that out, the beautiful thing about multiplication is you can do it in a string. That comes up to about 7.8 feet of head. We're going to call it 8 feet ahead for good measure. 3 gallons a minute at 8 feet of head. And if I were to put it on my chart, I'm looking at it right there. If I'm using the 0015, friends and neighbors, what speed am I going to set that at? Chime in on your question chat section. I'd love to hear what you have to say. Which one will it be? Which one will it be? Who's got it? Who's got the answer out there in the real world? Let's see what you got. Who's got it? Who's got it? Just type it on in when you know.
All quiet on the Western Front.
All quiet on the Western Front, people. Let me get. It's going to either be low, medium, or high. Pick one, okay? All right. We've got a medium. We've got a medium. We've got a medium. All right. We've got a medium. We got a lot of mediums here. I'm going to tell you this. I'm going to shock you. I'm going to go low. Yeah, Brad's got it. I'm going to go low speed here. Why would we go low speed? Obviously that 3 gallons a minute, 8 feet ahead is above the blue L line. It's above the low speed line. Why would we go L? Why wouldn't we go M and be sure? Well, remember, we estimated head on the high side. We estimated the head as if the flow rate were in fact 4 gallons a minute, but in reality, the flow rate is 3 gallons a minute. I will tell you, if we were to math the head out the right way, we come up using actual flow rates and pressure loss per foot of pipe based on the flow rate, the actual flow rate, we'd actually have a head loss of about 4 feet ahead. Done this example many times, that's why I know. But in reality, 3 gallons a minute at 4 feet ahead is going to be where we want to be. So low is going to be more than fine. Now, just for giggles and grins, if that 3 gallons a minute at 8 feet ahead was in fact dead on accurate, it was the true number, I'd still pick low because I'm close enough, right? I'm close enough. First off, that 30,000 was based on a heat loss. That heat loss is going to be 30,000 BTUs only under design conditions, which by definition is about that much of the year. The rest of the heating season, that low is going to be more than enough flow. And that low setting is going to give me more than enough flow. And if I have enough horsepower in the boiler to deal with it, you know what? The worst thing that would happen in this zone under design conditions is that probably the delta T might stretch out to 22 or 23 degrees. That might be the worst thing that would happen here if that 3 gallons a minute at 8 foot ahead was dead on accurate. So in this case, I'm good with low. There's no need to overpump this. There's no need to overpump this because if I do, bad things might happen. So let's take a look at what those bad things might be. What I've got here is I use my B&G system sizer wheel to extrapolate out the system curve. Scale 5 on the B&G system sizer wheel will allow you to do that. So I know the flow, I know 3 gallons a minute, 8 foot ahead. I know that's what I calculated. Based on that, I can figure out mathematically what the head loss is at 1 gallon a minute, what it is at 2, what it is at 3, 4, and 5. And I create what's called a system curve. And the cool thing about a system curve is when you connect the dots, excuse my shakiness, when you connect the dots, you will see that the system will actually operate where the system curve intersects the pump curve that you've chosen. All right, it will intersect the pump curve and that's where it's actually going to work. So, okay, if I choose low, I'm maybe what, 2.9, 2.8 at a little under 8 feet ahead. Hey, I'm good. That's going to be fine. If I set it at medium speed, I'm actually going to be over pumping to the tune of 4 gallons a minute. That's a 25% increase. I'm sorry, that's a 33% increase in flow over what I need. That's going to result in an actual delta that's going to translate to about a 25% lower delta T under design conditions. So instead of a 20-degree delta T, I'm going to have a 15-degree delta T at best. And now we're starting to get into this short cycling, even under design conditions that we might not want. And if you went to high speed, contractor no callback mode or ramming speed, I'm up to almost 5 gallons a minute. And now I'm really over pumping and my delta T gets real small and I'm really going to start to short cycle. So those are some of the ramifications of saying, I want to be safe. I'm going to go up one. So that's just kind of the way it is. All right. That's how this thing works. So will it work? I mean, if we have to define what work means. It'll work. I mean, people will not freeze to death and blame you. And no one is ever going to call you up and say, hey, pal, you promised me a 20-degree delta T. It's only 15. Get out here and fix it now. You're never going to get that phone call. However, what is happening is we are encouraging that incredible shrinking delta T, which, gentlemen and ladies, is an efficiency killer. All right. It promotes short cycling and it wears parts out. Other than that, it's not a big deal. But I can adjust that universal hydronics formula to because it's an algebraic formula. I can adjust it to isolate for anything. In this case, delta T equals BTUH divided by GPM, done first, and then that number is going to be divided by 500. That's just kind of how it works out mathematically. So if I had set that at high and was running at about 5 gallons a minute, the best delta T I'm ever going to see under design conditions, my friends, is about 12 degrees. That's the best delta T I'm ever going to see. And that's only for like 2% of the heating season. For the rest of the heating season, it's going to be less than 12. We will spend almost all of the heating season with a system delta T in that zone of less than 10. I mean, we're talking about single digits, and we're going to spend more than half of it with a delta T of less than 5. Now, talk about short cycling. That doesn't help anybody at all. If we went to medium speed, it's a little bit better, but as we said earlier, that delta T is going to be 15 degrees max. Again, most of that heating season, we're going to be spending, we're going to have a delta T of less than 5 because we will spend a good 50% of the heating season at 1/3 load or less, and 1/3 load here is 10,000 BTUs. All right, so we're going to be at less than 5 degree delta T most of the heating season. That's going to happen no matter what speed we choose. Let's just not make it worse, okay? If we do the math and actually figure out that, yeah, we can use low speed here, we will actually we will have the system in a better situation, all right? Now, before we start saying, well, will variable speed take care of this? Depends. It depends. We still got to know what we're doing, okay? And we're going to get into that as well. How about this one? I need a high speed. I'll need high speed for zone valves because I got all those zone valves and all that head loss and all that one pump for all those zone valves. I'm definitely going to need more power there, right? Well, let's take a gander. Here's an important truth about zone valve systems is that it is a parallel piping system. We do not have to add the head of all of the zones up. So like I said, if I have 3 zones, one has 3 foot ahead, one has 4 foot ahead, one has 5 foot ahead. All right. 3 and 4 is 7 and 5 is 12. I don't have to have a circulator that can do 12 feet ahead. All right. Because it's a parallel piping system. If my circulator at that point, 3, 4, and 5 foot ahead for 3 different zones, if my circulator can overcome 5 foot ahead, can it not also overcome 4 foot ahead and 3 foot ahead? All right. I don't have to add them all up. In a parallel piping system, the head is not cumulative. The head is, let's pick the worst case one and deal with that. Flow is cumulative, right? Flow is cumulative. I have to get the total flow, all right? Because I gotta consider that all zones are going to be calling at once at some point. So I'm going to have the flow rate for zone 1, the flow rate for zone 2, and the flow rate for zone 3 at one time. So my flow rate through all of the zones I add up. That's the flow the circulator has to deal with. The head loss the circulator has to deal with is only the worst case head loss zone. Let me know, friends, if that makes sense to you. We see an awful lot of circulator selection circulator selections for zone valve jobs go haywire simply because people are adding the head together as well as the flow. Don't add the head together. Worst case zone only, but do add the flow together. So let me know if that makes sense at you. All right. And as you're responding, because I know you will out there, people, I know you're out there listening to me, we are going to pay a visit to the Takeo Mystery Theater. Jason, you've never been to the Takeo Mystery Theater. This is a special treat for you.
This will be a first for me, John. I don't know what to expect here.
It's a mystery. Okay, that's why we call it Mystery Theater. What is Takeo Mystery Theater? We're going to throw a mystery at you and see if you can put your Columbo skills to work out there, friends, and try and solve this mystery. It's a mystery. And this is a real mystery. This actually happened to me many, many years ago. A very good friend of mine, a good customer out in Connecticut, called me up and said, "Hey, John, we got a problem." And his name was Ed. And I said, "Ed, you're my pal. If you got a problem, that means I got a problem. We're in this together. Let's see if we can't figure it out." And he said, "A customer of mine, and you know who he is. You've met him many times. He's been to your classes." And I knew the guy, great guy, excellent installer, excellent contractor. Guy did things first class all the way. He said, well, he changed out a boiler. All he did was change the boiler. He put in a new expansion tank, new air separator, new circulator, new zone valves. Or no, I'm sorry. He kept the old zone valves. And all of a sudden, we had a problem. The zone valves were banging. So it was a 90,000 BTU boiler, all new accessories, 5 zone valves. And after the change out, the zone valves would bang. Before the change out, the zone valves didn't bang. Before the change out, no banging zone valves. After the change out, zone valves bang. All right. And all he did, he changed the boiler, he changed the circulator, he changed the expansion tank. Some reason Ed was convinced it was the expansion tank that was causing the problem. I said, no, I don't think so. The only thing he kept were the zone valves. So if you guys out there want to put on your inner Columbo, what do you think's going on here? I'd like to hear from you folks out there in webinar land. What do you think's going on here? All right. Joe, knowing what you know right now, just based on what you see on the screen, if you had to diagnose this, why do you think the zone valves are banging? I hope I haven't put everybody to sleep, because mystery theaters are exciting. But I want to know, what do you guys think out there? Why are these zone valves banging? What would possibly cause them to bang? Direction of the pump. Good call there. Nope, pump's pumping in the same direction as the old one was. All right, which is the right way. So it's not the direction of the pump. Maybe the new boiler has a lower pressure drop. Maybe it could, but I'd still not explaining the bang, why the zone valves would bang. Oh, Brad, you might be onto something there. Brad. Brad says excessive head. That's something worth investigating. So let's see what we got here. Let's see what we have here. So the original pump was a Takeo 110. Okay, that's this guy right over here, the Takeo 110. It's kind of like the B&G 100. High flow. We're out to about 33, 34 gallons a minute. Say 33 gallons a minute, that's 330,000 BTUs. That's a big honking pump in anybody's book. But check the curve. It's a low head circulator. It maxes out at what looks to be about 7 feet ahead. All right. So think about that for a minute. All right. So when he put in the new circulator, he put in a 0015, and it was a 3-speed circulator, and it was set to high speed, and the zone valves were banging. He set it to medium speed. The zone valves were banging. He set it to low speed. Still got some banging zone valves here, man. Still got some banging zone valves, which was interesting. It was interesting. So, Brad, I think you're onto something there. It might have to do with excessive head. So the more we talked, then Ed told me, what we did was we figured your pump was the problem. So we took out your pump and we put in a Grundfos 1558, and it's still banging. And I said, wait a minute, you got banging zone valves and you have, my competitor's pump in there? And he goes, yeah. I said, Ed, I don't see how we have a problem. He didn't like that, but hey, I wanted to prove a point. I said, no, Ed, who did you call? Who's your friend? Who's your buddy? You are. Okay, now we can work together to find a solution. But they were still banging, even at low, medium, and high speed. They were still banging. So again, we go back to that excessive head. Now we have to understand what happens when zone valves close, right? When zone valves close, what happens is that system curve that we showed you earlier, because I have basically a new system, all right? One zone closes, I got, in this case, I had 5 zones. One zone closes, I have 4 zones. I have a completely new and different system curve, but because the flow is lower, more often than not, that system curve is going to back up the pump curve. So lower flow, but higher head loss or head pressure differential created by that circulator. So I had to ask Ed a question. When do the zone valves bang? And he said, well, when they close, you doofus. I mean, maybe I did call the wrong guy. What are you talking about? He said, no, that's not what I'm asking. I said, when do the zone valves close? Like when all 5 are open and 1 or 2 closes, or in like say 2 or 3 are open and 1 or 2 close? And he goes, does that make a difference? I says, I think it might. Why don't you check it out? He says, yeah, I'm going to the job today. I'll get back to you. He calls me back the next morning and says, how the hell did you know? How did you know? I mean, you were dead on. All the zone valves open and 1 closed, no problems. When, I only had 3 open and then 1 or 2 closed, they banged like crazy. What's the problem? Well, again, Brad had it, excessive head. All right, so let's say 80,000 BTUs was the load. in each zone, call them about the same, about 5 foot ahead, 16,000 BTUs. If I was using that Takeo 110 and I extrapolated out the system curve, with all zones calling, I'm getting about 10 gallons a minute. All right. And at about, that looks like just about 6-7 feet ahead, with one zone calling, 16,000 BTUs, 1.6 GPM, I'm at about 7.5 feet ahead. Big change in flow, right? Big change in flow from 10 down to like 1.6 or 2. Big change in flow, very small change in head pressure differential, and still very, very low head. At that point, no banging. So there's no banging with the old circulator. When we put in the 0015 at high speed, all right, I needed 8 gallons a minute at 5 foot ahead. Where's my little marker here? 8 gallons a minute at 5 foot ahead. That's what I needed, right? But at high speed, I was actually giving it over 11 gallons a minute at just under 10 feet ahead. At just under 10 feet ahead. Now, as my zones close, all right, new system curves, and we're backing up the pump curve like so. So with just one zone calling, I might need to be down here at 1.6 at 5, but in reality, I'm way the heck up here at almost 3 gallons a minute and 15.5 feet ahead. Zone valves don't like banging against that kind of resistance. So once we got to about, I'm going to say probably right about here on that pump curve, things started to bang. And that's why the zone valve banged. And it was the same with the Grundfos. It was the same with ours. All right. In reality, a better selection might have been the 0010 at medium speed. That might have been a better choice for him. All right. Because now, all right, one zone calling, I might be right about here, a little bit, 9.5 feet ahead. That might have been the cutoff point. I might have been just fine there and given it enough flow. Now, could I go down to low? I could go down to low speed. All right. I could have gone down to low speed on the 0015 or the 1558, but this is a problem compared to where the pump curve is. All right. I may not be able to heat that structure with all zones calling under design conditions or when I reached a certain level of cold outside. Might be, hey, everything works great till I hit about 10 degrees and then all of a sudden I can't keep the house warm. That might be the explanation you would get there, or the complaint you would get there. Let me know if that makes sense, friends. Let me know if that works for you, because these are the system dynamics that we talked about that need to be understood. Zone valves don't bang because they're installed backwards. They don't. Sometimes they do, but that's the way they are. Zone valves don't bang because they're bad zone valves, and the circulator doesn't make zone valve bang because it's a bad circulator. It's simply a bad marriage. They shouldn't have gotten together. These two crazy kids shouldn't have gotten married, okay? It was a bad idea. So in this case, it was just the wrong circulator selection. So again, we had the same problem with the Grundfos, okay? Same thing. It was just no different, really. It was no different. So because the circulators are basically the same. Why would there be a difference, okay? But as Colombo used to always say, there's just one more thing. There's just one more thing, all right? If I had gone with that 0010 at medium speed, I think I'm going to be fine. At low speed, I might run into the same problem, but medium speed, I think that's going to work out just fine. So the 0010 3-speed, if you want to go AC, there's your solution. Does ECM make this all go away? Oh, I'm sorry, I want to show you the 007. 007 might have got her done too. Just a regular old 007 probably would have been the right circulator. There's a reason, friends, why the 007 is the #1 selling wet rotor circulator in North America, and it's not even close. It's because it's the perfect zone valve circulator, because it is a relatively speaking flat curve circulator, and its maximum head is less than 10 foot. Right? It very well, in this case, I would bet dollars to donuts that we'd be fine with the 007 here. We're going to over pump, okay? Doesn't help us with our delta T problem. We're going to over pump, but we'll be okay. All right, so that one would work very, very well. Big changes in flow, relatively speaking, small changes in head pressure differential. So I think the 007 would probably be all right. Does ECM solve the problem? Well, maybe yes, maybe no. We got to understand ECM isn't magic. ECM isn't, we call them smart pumps. Terrible name. They're not that smart. They're obedient, but they're not smart. They'll do what you tell them to do. Now, the 007E is simply the ECM version of the 007. Simple, single pump curve, no programming, no nothing, just let her rip. It's a 10-foot ahead constant pressure. So at that 10-foot of head setting, it will vary its speed. All right. So the 007, if I look at it, all right, these are my requirements. This is really where it's going to work. Again, that 10-foot ahead constant pressure line, we're hoping will not cause a problem. I'm still going to be over pumping. I may be on the edge of bang zone valves, maybe, maybe not. We'd have to see. We'd have to see. If you want a definite solution to this problem, and if you know the flow in head, you might be better served with the 3-setting circulators, the 0015E3. But now we have to understand what we're doing. It's a 3-setting circulator. The urge to set it to high is still there, but you'd still have to know your system dynamics and understand what circulator you're replacing. In this example, you'd set this thing to low, and now this circulator is going to vary its speed between this point and this point. It's just going to vary its speed back and forth. As zones open, it'll go faster. As zones close, it'll go slower along that constant pressure line. So under design conditions, we're going to have as close to a 20-degree delta T as we can. As it gets warmer out, the delta T will go down, but we're giving this thing a fighting chance. So in this example, I would say the 0015E3 is the best choice of any circulator out there. Next best would be either a 007 or the 0010 3-speed set to medium. Again, does this make sense to y'all? I'd love to hear some feedback because I've got 85 of you out there. I'm hoping every last one of you is paying attention and enthralled. Now, a lot of folks will say, well, what about delta T? Is delta T going to solve this problem? Delta T pumping, basically, the 0015E3, 007E, that is what we call delta P. It changes its speed to maintain a specific pressure differential in the system. Delta T pumping, our VT2218, and next year we got a great, oh my God, am I excited about next year with our new delta P pump, or delta T pump rather. Delta T will vary its speed to maintain a specific delta T within the system up until the point when it can and it reaches low speed. This is merely the optimal way there is of running a variable speed circulator because it's based on actual load, not just some inferred pressure differential, but it's based on the actual load and the changing load, which is important. And it's probably as close as we have, ladies and gentlemen, to a truly self-sizing circulator out there. A lot of people think, oh, I press the auto button, it sizes itself. That is not how it works. That's not how auto works. But this is based on GPM equals BTUH divided by delta T times 500. We know the BTU load is going to change based on zones opening and closing and based upon the weather. We know the BTU load is going to change. In that algebraic formula, GPM equals BTUH divided by delta T times 500. If the GPM is constant, as it would be with a fixed speed pump or even with a delta P pump, if the GPM is constant and the BTU load changes, the delta T has to change with the BTU load. Okay, it has to. If the BTU load goes down, I'm still getting X amount of flow. The BTU has to go. The delta T has to go down. If, however, we hold the delta T constant and we change the flow, the flow will change then in relation to the load. So as the load goes down, the flow goes down. As the load goes up, the flow goes up, both with zones opening and closing, but also based upon the weather, how cold it is outside, because the BTU load is going to be impacted by the weather. Now, the pump doesn't have an outdoor sensor. It's inferring the load based on the return water temperature and delta T. So it's a slick, very, very accurate way to vary the speed of a variable speed circulator. And it is as close as we have to a self-sizing circulator as there is. So what Ed could have done is put a delta T pump on there, sensor on the supply, sensor on the common return, all right? And that circulator would have sized itself. Now, if he started this thing up in the fall when the load is still low, probably wouldn't have gotten above minimum speed. All right, and and maybe not. It may have been running too fast even for then. He may not have had a 20-degree delta T. But as it got colder out and colder out, that circulator would ramp up and go a little faster. So in theory, yes, a delta T pump would solve that problem. Here we have 8 gallons a minute at 5 foot ahead. So I'm right in the sweet spot here. All zones calling. Okay, I'm working along a pump curve kind of like this, and we extrapolate that up to the upper end. At full speed, this thing's 59 degrees, the VT2218, I'm sorry, 59 watts. And at minimum speed, it's 9 watts. This looks like it's right in the middle, so it might be about 30 some odd watts, maybe 30 watts or so under, under design conditions. This is one zone calling. Under design conditions, that smallest zone, that might be about 13 watts. So under design conditions, I'm going between 13 and 30 watts. Now, as it gets warmer out, both of those lines are going to go down because the BT load is less. As it gets warmer out, both of those lines are going to go down. So if, say, I had 6 gallons a minute under design conditions with all zones calling, all right, I'm going to have a line, I'm going to be working here, so that may be about 20 watts. At 50% load, look where I am. I'm actually down here. You know what? At 50% load, I've got a 9-watt fixed speed pump. That's not bad, people. That's not bad. I'm not going to have a 20-degree delta T, but I'm not going to have a 5-degree delta T either. So that's why we use delta T pumps. It's a great way to run this circulator and have it run as accurately as possible to help minimize. We can't eliminate it, but we can minimize short cycling to a very, very impactful degree. Let me know if that makes sense to you folks. All right. Henry's out there, says in response to something earlier, but let me know if that's making sense to you. All right. Again, self-sizing, but we do have, again, we can't go slower than slow. We can't go slower than minimum. When we look at ECM circulators, we also have some bigger guns too. We go to the VT2218, the 0018E, the 0015E3, etc., are all built on that one platform. We have some bigger guns, the 26E and the 34E. The 0026E is 26 foot ahead out to 44 gallons a minute. The 34E is 36 foot ahead out to 50 gallons. Do a little bit more. These are bigger guns for us. Where might we use these? Well, the extended header is really a great application for this type of a circulator. The extended header, where the header goes throughout the building. So this is light commercial or heavy duty residential, like some of these mansions that you run into, or the really big, expensive, weekend chalets that people have, all right? Where you've got, in this case, I've got zone valves, but they're all throughout the structure. They're all throughout the structure in an extended header piped in a reverse return manner. So in this case, I'm just going to give you some examples of what each separate heating element has for flow and head. So I get 2 at 7, 2 at 9, 2 at 5, 2 at 7, blah, 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 2 at 9. All right. And I keep going through all this. And then I got to figure out, based on what I'm looking at, for head loss, I want to size that circulator to my worst case head loss zone. And my worst case head loss zone is going to be that guy, 3 gallons a minute at 9 foot ahead. So I'm going to start with 9 foot ahead. I also have to factor in all of my supply and return piping. So basically all of the piping that's going this way and the piping back that way. So my reverse return piping, I got to factor that in as well. So I want to size the circulator. I'm starting with 9 foot ahead, but I have to add the other head in, which is in series, which is different than parallel. I have to add that other head, which is in series, okay? And I have to add the flow together. If I add all that flow together, I got 24 gallons a minute, 9 foot ahead on that worst case zone. My supply and return piping, let's call it another 9 foot ahead. So my circulator is going to have to do 24 gallons a minute at 18 feet ahead. If I look at the 0034E under constant pressure, which is a good one for zone valves, constant pressure setting, well, 24 gallons a minute at 18 feet ahead is okay, pretty much right there. That C3 setting, 18 foot ahead, that's going to work just fine. I also have the ability, I could put this in what we call Takeo adapt. Now, this is an instance where the auto function might work, provided that the circulator is running constantly. All right. Any of these auto modes that you see out there, no matter who makes them, for them to really do much of anything, the circulator has to run continuously. Like as soon as you turn the system on in the fall, it runs and it doesn't shut off till you turn the system off in the spring. All right, that's constant circulation. It has to run on constant circulation for it to adapt or learn a blessed thing. So I could put it here, and again, yeah, as long as I'm within that purple wedge, it will adapt. It will work on it'll work on this proportional curve, which in this type of a situation is not a bad one. So it'll work on this proportional curve right here. All right. But as it runs and as it gets warmer out, and if my drops in flow are enough and they last long enough, I might drop down from, let's say, this this performance curve here down, this performance curve here down to this performance curve between these two. I can't draw without the pen, but ideally what I'm going to want to do is automatically bop in between these two performance curves. Let's try that again. All right, between this performance curve and that performance curve. There we go. Now you can see it. All right, that's kind of what I would ideally like to do when we're we're operating at a stasis or at a stat or kind of a constant level. During the winter, it's going to bop up and down between 1, maybe 2, but probably just between 2. It's going to bop between 2, maybe 3 of those curves, maybe 3 of those curves. Is that right? Right. All right. Questions out there, folks? I'm hopeful that this has been useful for you. I got some key takeaways for you to think about from today. Just some key takeaways. The first one is understand what 3-speed pumps are and what they aren't. They're not a cure-all. I hate it when people say, well, it's the only pump you'll ever need. It's got 3 speeds. No. Systems have dynamics, and those dynamics have to be understood and respected. If you put in a steep curve pump like a 0015 or a 1558 in place of a flat curve pump like that old B&G 100 or Takeo 110, you're inviting issues where there were none before. And usually, this is again makes me crazy. But people say, "Oh well, when the zone valves are banging in that situation, someone will say, well, that guy should have put in a pressure differential bypass valve like they do in Europe. Didn't that guy know anything?" No, they don't put in pressure differential bypass valves for that reason in Europe. Pressure differential bypass valve is a band-aid for a self-inflicted wound, and that self-inflicted wound, in the case of what we showed you in Takeo Mystery Theater, was the wrong pump for the job. Okay, that was a self-inflicted wound. So yeah, he could have put in a pressure differential bypass valve and solved the problem. But that's, again, why would you spend that kind of money, charge your customer that kind of money when you put in the wrong pump in the first place? At that point, the best thing to do is to take the wrong pump out and put the right pump in. So 3-speed pumps are not the cure-all. Watch out for contractor no callback mode, right? Ramming speed, again, you see them out there, folks. You see them out there. How often are those things set to high speed? Because, hey, it works. Nobody's complaining. Nobody's freezing to death and blaming me. Yeah, the system's not as efficient as it could be or should be, but that's just the luck of the draw, right? If we understand the dynamics and understand what happens when we do things, all of a sudden, issues start to make sense, okay? Issues start to make sense. If we short cycle like crazy because we've set it to contractor no callback mode, well, it's what's going on. The system's not as efficient as it could be or should be because we're over pumping, in some cases drastically. All right, 2 little clicks have a big impact, man, can have a big impact on overall system efficiency. And if we find that expensive or key components are wearing out prematurely, 3 to 5 years, when they never did before, it could be that, yeah, these things are junk, or it could be that maybe we're over pumping and short cycling things into an early grave. You got to think about that. That is a very distinct possibility. All right. And last 2 items, ECM pumps, we call them smart pumps. They're not. You still have to know what to do with them. You can't just stick them in, press a button, and hope for the best. You really do need to understand how they're applied, what they'll do, and what they won't do. They don't think for you. They don't take the thinking out of it. They're not magic. They're not even that smart. Okay, they really aren't. They'll do what you tell them to do. They are, my friends, obedient. Okay, they are obedient. They'll do what you tell them to do. And you look at a Delta T pump, a VT2218, and that's the cool thing we got coming next year, people. Those pumps are smarter than the others, but overall, they're all pretty obedient. They'll do what you tell them to do. And if you tell them to do the right things, they'll do the right things for you. And that's really the key to understanding ECM technology. Don't expect them to think for you. They can't. They're not that smart. All righty. Well, Colombo, we say thank you. How was that today for you folks? Let me ask, let's throw any questions open to the crew. Anything you want to ask or comment, we'd love to hear from you. So again, now it's time to ask some questions if you have them. Let me know, was this useful stuff for you? Was this something you can apply starting today, starting tomorrow on your job sites? To me, that's the acid test for any training that we do. Did you learn something today that you can use tomorrow? That's kind of the important thing. That it gratifies us and make sure, like for Jason and I, make sure we're doing the right things for you. But as Chris says, yeah, it's pretty cool. All right, great, Chris. Thanks, man. I appreciate that. Again, let me know, what did you, maybe this is the key. Type in one thing you learned today that you didn't know, if there was one. If there wasn't one, well, okay. But if there's one thing you learned today, just type it in for me. We'd appreciate that. And again, and any questions you have on this topic or any other topic, now's a really good time to ask them. I think we've got a bashful group here today. I don't know. What do you think, Jay?
You know, John, once again, you delivered a master class in 3-speed Circs, but you know, it has been absolutely quiet in the chats today. That could be a good thing. You know, hey, you did a good job.
Who knows? Who knows?
Right.
Let's so. We got a nice overview from Brad. Thank you, Brad. I appreciate that. Again, just one thing. One thing, folks, that you learned. Very good breakdown of the use of pumps. Not sure this was the chat. Aha, there you go, Frederick. Frederick figured it out. Wasn't sure that this was the chat. Okay. We try to make sure we understand. We put that out in ahead of time, but it was the chat question section. So great. T-Lo says going to miss that 007 circulator. I'm with you, T, baby. I'm with you. Yeah, that's I mean, the company was built on the 007 going back 50 years. 1975 when that thing first came out. And it's going to be a sad day when the last one comes off the line. Bittersweet day, I think. It'd be sad, but also, hey, it's turning the page and going into a new chapter of technology and efficiency. So yeah, it's going to be an interesting day. I hope I'll be around. So, all right, folks. Well, great. Hey, thank you so much for the gift of your time, my friends. I really appreciate it. J-Dog, I did it twice in one day, man. J-Dog.
Hey,
J-Dog.
I like it. It's what
right.
my parents would call me that. So
You're
very
really
good,
okay.
John.
You got,
yeah.
I think I'd like to hang with your parents, man. But we'll see you tomorrow out in Cranston. We have our factory training class starting Thursday, Friday. We got 40 plus contractors and wholesalers and reps coming in to spend a couple of days with Jason, Dave, and I at the factory for 2 days of training. So if you thought this was fun, just imagine doing this for 2 full days. Oh my God. Like a hydronics bacchanalia. And if you don't know what a bacchanalia is, look it up and then you'll think of Jason and I. But anyway, cool. Hey, folks, thank you so much. Jason, travel safe. We'll see you tomorrow.
See you.
And thank you everyone for being with us. Enjoy the rest of your Takeo Tuesday.
Bye-bye now.